Okay, so we been talking about gases, obviously, in this last chapter. We covered a number of, obviously, gas laws along the way that we talked about last time. We went through the ideal gas law. We went through the combined gas law. We also kind of finished up again talking about last time about stoichiometry that involves gases. So remember when we're dealing with sort of stoichiometry and gases, it pretty much works the same way as basic stoichiometry problems, which basically means you really do follow those sort of 4 steps that we talked about. And again, a reminder that basically with any type of stoichiometry problem, right, it doesn't work unless we start with the balanced equation. We then want to convert to moles. And a lot of times in gas stoichiometry problems, this part is sometimes like a traditional part where we do go from kind of grams to moles. Occasionally, you may have to, as we talked about before, use the ideal gas law up front in this type of calculation. And in that case, you would be solving for moles, and then would be PV over RT. So that would be sort of an alternative. I would say a lot less sort of used up front, the ideal gas law in a gas stoichiometry problem. A lot of times you use sort of at the end of the problem, but definitely could potentially be used sort of up front. Again, maybe you're told how many liters of a gas was produced, and you want to know how many maybe grams of a reactant you started with. So you could potentially kind of go into the ideal gas law up front and kind of work backwards in the stoichiometry problem. The third part is, again, just really the stoichiometry part of it is the mole to mole relationship. Again, obviously the moles of whatever you were given and the moles of whatever you're trying to find. And I would say in sort of a gas stoichiometry problem, more common than maybe using the ideal gas law up here would be using it in this step here. Again, using sort of PV equals nRT. And I would say probably in most cases, volume is a very common one that you are sort of trying to find. The volume of a gas is produced or something of that nature. And again, at this point, you would have the moles from the previous step, R, T, and P. T and P would be given to you. R obviously is a gas constant, which you always have. So, these are sort of the common steps in a gas stoichiometry problem. They're really sort of the same steps that we do in a sort of regular stoichiometry problem, both sort of grams to moles type of problem, or even solution stoichiometry. The real difference in all these is sort of how you get to that convert to moles part, maybe, or at the end part. And again, like I said, probably in a lot of cases, this is sort of what you would do at the end. Also, a reminder that, even though we maybe sometimes think about other stoichiometry problems like solution stoichiometry or gas stoichiometry, it is possible again to have a limiting reagent type problem in one of these. And again, you would just follow the same rules as we talked about when we talked about limiting reagents. If you look at the information sort of given to you in the problem and you really have enough information to get to moles of all the reactants, that's sort of the key there for knowing it's a limiting reagent problem, and that you need to sort of figure out which one is the limiting reagent, is that idea. However, whatever information they give you, again, if you have enough information to get to the moles of all the reactants, that basically tells you it's a limiting reagent problem. You need to obviously figure out which one is the limiting reagent, and that would determine, obviously, which one would determine how much product you would make. If it's a sort of typical stoichiometry problem where you again only have enough information to get the moles of one reactant or one sort of person in the reactant side there, then it's just a basic stoichiometry problem. Any questions on that stuff we talked about sort of last time? Okay, so where we left off is the next sort of topic there involving obviously gases, and that is Dalton's law of partial pressure. And it sounds like it's kind of super scary, the Dalton's law of partial pressures, but it's not too bad. Couple of things about this here. Let's get some things out of the way so we could actually see. All right. Now, when we think about sort of gases, oftentimes they really do come as mixtures of gases. So a lot of times they do come as a mixture of gas. So when we have a container, say like this container here, that's got the red circles going on down there, if we were to try to figure out what is the total pressure in that particular container, because there's only really one gas molecule flying around there, the total pressure of that entire container would be made up of the pressure of gas one, I guess it would be the red circles. If we were looking at, say, this container over here with the green gas molecules basically flying around, and we wanted to know really, what is the total pressure, really the total pressure in that particular container would be a result of pretty much all the pressure of those green guys that are basically going around. Now, if we put both of these gas in the same container, we now have a situation where we obviously have a mixture of gases. So basically the green guys are flying around doing some collisions, causing some pressure. We got some red guys flying around doing some collisions, causing some pressure. And now what we end up with is actually the total pressure is a result of both gases that are in this container, so P1 and P2 in this example. Now, because there's multiple gases flying around and multiple gases causing collisions and causing pressure, these are what are referred to as partial pressures. They're partial pressures because when you add all of the partial pressures up, it will equal the total pressure of that gas mixture. So, that's basically what partial pressures is. They're each basically contributing to the overall pressure of that container because they are each flying around. One of the nice things about sort of thinking about things as ideal gases is that even though they're in the same container, we can really treat these gases as if they were in there by themselves. So the green guys by themselves, the red guys flying around by themselves, even though they're technically flying around together. Part of what makes something an ideal gas, and I might have touched upon it the other day, is the idea that there's kind of no interaction between different gas molecules. So even though we got multiple different gas molecules flying around in the same container, we're assuming that there's kind of like no real interaction that's happening between the different gas molecules. So what that means is we can essentially find the pressure for each of these gases separately. And how we do that, the most common way is actually just to use the ideal gas law, and that is PV is equal to nRT. We would solve for P for both gases. So P1, for example, would be nRT over V. P2 would be nRT over V. We basically could solve individually these gases, again, treating them as ideal gases, which means even though they're in the same container and they're not interacting with each other. And then basically we could just simply add up both of those numbers, and that will give us our total pressure. The other nice thing about sort of a mixture of gas situation is basically volume and temperature are constant for both of those things. And what I mean by that is they are both pretty much sitting in the same container, which means the volume's the same for every gas flying around in there. And that container is probably sitting in the same room as everybody else. And that means that the temperature is usually the same for both. So really, when we think about the ideal gas law and using it to solve for the partial pressures in this situation, really the only thing that's going to be different in each of these cases is usually the moles of the gas that are flying around. So usually the nice thing about these guys is we really just need to figure out, what is the moles of each gas is around for each of the ones that are flying around that mixture. We essentially just need to put it into the ideal gas law twice if there's two gases, three times if there's three gases, and so forth, and basically just solve for each of the pressures individually. Again, that would represent what is referred to as the partial pressures of each of those guys. And then to find the total pressure, again, like I said, we simply would just add them back together. Any questions on that there? All right. So as I mentioned before, really the easiest way there is to do our ideal gas law and sort of solve it and then add them back together. Now, there's also another way that we could kind of figure out partial pressures or partial pressure sort of situations. And sometimes we may not be able to use the ideal gas law. So what do I mean by that? I mean, there are certain situations where you just don't have enough information. So you don't have enough info here to actually use the ideal gas law to help you solve it. So sometimes there's another way that you could kind of do that. And another way that you could kind of do that is to use something that we saw, I believe, in the last chapter. And if you remember, this is our mole fraction, right? So this is our mole fraction. These are the moles of A in this example, and that's the total moles. So if you remember, the mole fraction is really sort of a percentage without the percentage. So it's basically figuring out the percentage of each of the moles of the gases that are there and not multiplying by 1,000, or 1,000, not multiplying by 100, that would be good. And you can figure out the mole fraction. So if we don't have enough information to use ideal gas law, this could be a situation where maybe they don't tell you the temperature, maybe they don't tell you the volume or something of that nature, but maybe they tell you how many moles of each gas you have, or maybe they tell you how many grams of each gas you have, and maybe they give you like the total pressure. You can use sort of the mole fraction, and this version of the equation here, which is basically the guy on the bottom here. This is the partial pressure of the gas you're interested in. So that's the partial pressure of the gas of interest is equal to the mole fraction of that gas times the total pressure. So if you remember, like I said, mole fraction is kind of like a percentage. So really you're taking the percentage of that gas times the total pressure, and it'll give you basically the partial pressure. So this is a nice little formula here where, you know, you can sort of still figure out partial pressures, total pressures, as long as you have really some type of information to get to grams or moles, or some type of information again about total pressure, or even if you have information about one of the partial pressures and some like mole information, you could do that as well. Any questions on that? So these are two sort of distinct ways that you can figure out the partial pressures of gas. When should you use each of these? It's really based on the information. So if you see you have enough information to go into the ideal gas law, you should go into the ideal gas law. If you see you really don't have enough information to go into the ideal gas law, but again, you got some mole information, some type of pressure information, then probably the equation with the mole fraction is probably the way to go in that sort of situation. Any questions on that? All right, so let's try a couple here. We have 5 grams of helium is mixed with 5 grams of neon in a 2.5 liter container at 27 degrees Celsius. Calculate the partial pressures of each gas and also the total pressure. So a couple things you might need. Helium, I think, is still 4.003 grams per mole. Our good friend neon is 2018, I believe, grams per mole. And I think that is all you need. That. So we should be looking for kind of 3 answers here. We're looking for the partial pressure of helium, for the partial pressure of neon, and we're looking for the total pressure. So take a few minutes here and see what you come up with. Okay, so let's take a look. So this is definitely a sort of partial pressure mixture of gases type situation. We basically got one container here, and flying around that container is some neon gas making some collisions, causing some pressure. Along with it is some helium that's having a fun time flying around there, also doing some collisions, causing some pressures. Now, because again, they are both really in the same container, As we talked about before, they're both at the same temperature, which is 27 degrees Celsius. They are both obviously in the same container, which has the same volume. That's 2.5 liters. So again, that is pretty much the same for both. In this case, we do have enough information really to use the ideal gas law. We would be solving for pressure for each gas. We have the volume, we have the temperature given to us. R is obviously a constant. Again, the one thing we're sort of missing here, which is very common in these type of problems, is the moles of each gas. So that's definitely what we'd want to start with first here. So using the molar mass from the periodic table, we could get our moles of helium, and that's going to be our 5 grams of helium divided by our molar mass, 4.003 grams per mole. Grams going to cancel, so dividing that out gets us something like 1.25 moles of helium. While we're here and we know we're going to really need to do that for neon as well, we might as well do that conversion too. So the moles of neon going to be also 5 grams in this case, dividing by the molar mass of neon, which is our 2018 grams per mole. Again, our grams canceling out, and looks like 0.248 moles of neon. So by doing those calculations, we've now got really the moles of each gas, which is essentially what we were missing. First off, any questions on that right there? So really, since it's the ideal gas law, we got to be careful of units. And in this case, it looks like temperatures are other kind of critical thing here. We do obviously need to add 273 to it to convert that guy into Kelvin. Looks like that might be a 300 Kelvin. R again is a constant, so we always have that number. And at this point, we really can now essentially just do 2 separate calculations. So the first one we're going to do is going to solve for helium. So again, putting in our numbers to the rearranging here, right, that the pressure is equal to nRT divided by V. Our moles of helium is 1.25. Our R is 0.08206 liters atmosphere Kelvin mole. Our temp is 300 Kelvin. That's all going to be divided by our volume in this case, which was 2.50 liters. At this point, unit-wise, we got some moles canceling. We got some Kelvin canceling. I missed it. We'll try again. And we got some liters canceling. That's going to leave us atmospheres, which is the only one left over, which is good because we are solving for a pressure. And if we do all that math there, take our 1.25 times 0.08206 times 300 divided by 2.5, looks like we get 12.3. Again, the units here would be atmospheres. Any questions on that calculation there? This number would represent what is known as the partial pressure of helium in this mixture. We would do pretty much dead on same calculation here for neon. Really, the only thing that's going to change is we obviously want to use the moles of neon in this case. So we'll put that number in here. Again, because they're in the same container, pretty much everything else going to be the same. Again, all divided by 2.5 liters. Same cancellation going to happen. Again, really going to only leave us there. Our atmosphere is up on top. That's a funky neon I just did there. That looks like we get 2.44 atmospheres here for neon. And again, this would be what is considered the partial pressure of neon in this case. Any questions so far on those 2 calculations? All right, so obviously the last thing that we're looking for is actually the total pressure in this case. So the total pressure, obviously in our little picture here, is made up of helium bouncing around and causing collisions, neon bouncing around and causing collisions. So it is made up basically of the partial pressure of helium plus the partial pressure of neon. So simply at this point, we would just add these guys together. And looks like we end up with something like 14.7 atmospheres as our total pressure here. Any questions on where any numbers came from, why we did anything here? So what do we see here if we kind of do a little analyzation, and we'll actually determine, sort of why this is here, or we'll see why this is in just a sec, but we'll kind of preview it here since we have the numbers in front of us. Well, the major contributor to this pressure here in this mixture is helium. And you may be wondering, why is helium the major contributor to the pressure? And as we will see very shortly in a few slides down the road, it is because of the molar mass of helium versus the molar mass of neon. We see that helium is a much lighter gas, which, as we'll talk about, will translate into helium being able to fly around faster, which means it's able to fly around faster than neon. And because it's able to fly around faster than neon, it's probably going to be the one making more collisions and contributing to more of the pressure that we see in this particular mixture. Any questions on that there? Okay, then let's try another one here, see what you come up with. A sample of natural gas contains 8.24 moles of methane, 0.421 moles of ethane. I'm going to try to not fail organic here, and 0.116 moles of methane, ethane, propane. Let's go with that. If the total pressure of the gases is 1.3 atmospheres, what is the partial pressure of propane? See, I did not too bad there. I just could read ahead. All right, take a few minutes here, see what you come up with. This particular one. Now, this one we have obviously a mixture in natural gas of some methane, some ethane, and some propane. Now, in this particular case, we obviously got no information. We don't know what the temperature is. We really don't know the volume is. That's going to pretty much eliminate PV equals nRT usefulness here, because we really don't have any numbers to sort of use that with. We definitely have moles, and we do have one piece of pressure information given to us, which is that's the total pressure here is equal to, what we got there, 1.37 atmospheres. So we got moles and everything. So we do want to use, obviously, that equation that we saw that will allow us to do that, which again is the partial pressure of the gas we're interested in will equal the mole fraction of that gas times the total pressure. So we definitely need to kind of figure out some mole fractions going on here. If we do that, what we got going here, we could add up our total moles. So the total moles in this case would be, it looks like we got 8.24 plus 0.421 plus 0.116 in this case. And if we add all those good guys up there, that's going to give us 8.24 plus 0.421 and 8.116. Looks like 8.777, looks like. So we could start obviously with the one we're interested in, which is propane. So to find the mole fraction of propane, which is C3H8, we would take the moles of propane, which was 0.116. We would divide it again by the total moles over here that we just calculated, 8.777. And if we do that, 116 divided by 8.777 gets us something like 0.0132, or really about 1.3%. is the mole fraction there of our propane. We then can use our formula here for propane. That means that the partial pressure of propane would equal the mole fraction of propane times the total pressure that was given to us in the problem. And if we do that, it looks like we're shooting at, try that again here. I don't think I got the right number there. Try it one more time. 0.0132 times total pressure 1.37. Looks like 0.0. We'll call it 181, and these would be atmospheres. Any questions on that calculation there? Now, if we wanted to, we could definitely do it for all the other gases as well. We could have done, it didn't ask us to do that, but if we wanted to do ethane, for example, we would find the mole fraction of ethane, which is 0.421 divided by 8.77. And that would get us 0.421 times 8.777. I think I lost a 7 there. There we go. Gets me 6.35. If I did that right, I don't think so. I think I'm hitting the wrong buttons on my calculator today. I'm going to try that again. At least I recognize it, I suppose. That's good. All right. Now, if you punch in the right numbers there, you don't get that for sure. Let's erase that. It's a good thing I'm using a calculator, I suppose, huh? All right. Try this again. All right. Actually hit the divide button, I think helps. 0.04. We'll call it 80. And again, we could then find the partial pressure of our ethane, which is 0.048, or really about 4.8%, times 1.37 would tell us the partial pressure of that particular gas would be 0.0657. At this point, you could actually do one more for methane if you wanted to, or because methane is the only gas left, you actually could add both of these together and subtract it from the total pressure, and you'll get the answer as well. So that's another way you could get to there, or again, just continue down the mole fraction way. Any questions on this type of partial pressure type problem? So far we've seen a couple different types of partial pressure problems. One, obviously, where you have enough information, you could just ideal gas law for everybody individually and then add them together. Here, you don't have enough information really to use the ideal gas law, but you do have mole information. And the key with that is you need some type of pressure information, either a partial pressure or total pressure sort of given to you. And you could use, obviously, the mole fraction. Another very common situation where we end up with sort of a mixture of gas happens a lot in the laboratory, actually, when you're doing experiments. So, for example, if we did this experiment here, we basically took some potassium chlorate and heated it up in a test tube. What's going to happen is you're going to basically generate some oxygen gas here. You actually will get something like this when you do that. It's a decomposition reaction. This is a catalyst, not really involved. And when you heat it up, you get a little KCl action and you produce some oxygen gas. So as you're doing this, you're generating some of this O2 gas. It's going to obviously try to find an escape route, and it will find this escape route through obviously the tubing here. I'm not going to allow it to escape to the outside world, but it's basically going to follow all the way through here. And it will usually end up in this type of experiment into a bottle or a collection container. And usually we fill the collection container with water. And what happens is as the gas bubbles up, the water comes out, right? So H2O comes out of the bottle. Gas goes into the bottle, and you end up with this quote unquote empty space. It's really not empty. That is where your gas that you're collecting ends up, like the O2 in this example, basically ends up there. This is what is sometimes referred to as collecting a gas over water, or it's sometimes referred to as collecting a gas saturated with water vapor. So why is it saturated with water vapor? It is saturated with water vapor because when you do this reaction, there's going to be some heat or something associated probably with this reaction. Heat in liquid water will create its own gas, right? And that's going to create H2O in the gas form, also known as steam, right? And also known in this case as water vapor. So in this process, just by the process of how you collect basically the gas in this experiment, you're actually getting a 2-for-1 situation where you're getting sort of water vapor to come along for the ride, along with your O2 that will end up in that sort of empty spot. The problem with the extra gas here is you're not really interested in the water vapor. You're actually interested in really just the O2 gas in this experiment, which means we need to do some type of correction factor to basically get rid of the water part. And it's sometimes referred to, you'll see it as sort of an experiment. They'll sometimes say, what is the pressure of the dry gas? And sometimes they'll say that because you're basically need to correct for the water vapor and subtract it off. So the way that we do that is it's really a partial pressure situation. The total pressure in this situation is actually the pressure of the gas you're interested in plus the pressure of water. And again, this is what is referred to as the vapor pressure of water. How do you find the vapor pressure of water? Well, you look it up on a table usually. Yeah, so you usually look it up on a table. It's usually based on temperature. So you can actually look up this value typically on a table. We'll see a table here in just a second of what one looks like. So how can we use that value that we get in the table? Well, in an experiment, you obviously can get this value from a table. The total pressure is really the barometer reading that you would take in the laboratory. So you go over to the wall, read the barometer, which means you typically have the total pressure. It's basically atmospheric pressure in the room. And that means we can rearrange this and solve for the partial pressure of the gas you're interested in by really taking the total pressure, which is again the barometer reading, minus the vapor pressure of water, which you look up on a table. And this will basically correct for the amount of water vapor that was in that area that you collected. Because again, if you were doing an experiment like this, you're really interested in just the oxygen gas. You have really no interest in the actual water vapor. So this is, again, a very common sort of procedure that's done when gases are collected in the experiment, and it's sort of a common correction sort of factor. The good news is it's essentially just subtracting, so not too bad in that sense. Again, like I said, the vapor pressure of water can usually be found in a table such as this one. This one is not from your actual book, but you have a similar one in the chapter. Also, if you look at even in your lab manual, I think in the back of the book, your lab manual, kind of where the appendices are after the study assignments, there's a whole bunch of charts and tables. You'll actually find one there as well. But again, you can see it really is based off of temperature. So you would obviously, in an experiment like this, you would take the temperature of the room basically, and you would then go to the table here, look it up. You would do the subtraction. And again, it essentially is sort of like a correction value, if you will, for our correction factor for just the way the experiment was actually performed. So let's take a look at one like this and kind of see and dissect sort of how we know it's this sort of situation. So usually in the actual problem, like a textbook type problem, they give you kind of that idea in words. So when we read this, that a sample of oxygen gas was saturated with water vapor at 30 degrees Celsius, that right there, saturated with water vapor, that is like the big sort of indication that, hey, you're dealing with what we were just talking about. You got the total pressure is really the pressure of the gas you're interested in, plus that vapor pressure of water. Now, the other sort of common way that is sometimes worded is what I said a moment ago. Maybe it may say something like the gas was collected over water. So again, some type of mention of water vapor, some type of mention of collecting a gas over water or something like that. Those are big keyword factors that basically indicate that, you've got to do this kind of correction factor. So 30 degrees is important because if they didn't give us the value, you would go to that table and find it for 30 degrees Celsius. What is the vapor pressure of water? In this particular case, they gave us the total pressure is 753 torr. And this again here is the value that you would find on a table like we just saw on the previous slide, that 30 degrees, the vapor pressure of water is 31.824. So we essentially have this guy, we have this guy. So we could then kind of use that along with our specific gas here, which in this case is oxygen, plus this. Doing a little rearranging gets us the partial pressure of oxygen is, again, the total pressure minus the vapor pressure of water. Putting our numbers in gets us 753 torr minus the vapor pressure of water, which if it was not given to you, you would find in a book or a table. And looks like perhaps 721 torr. It does want, again, the units here in atmospheres. So a reminder that the 760 number is our important conversion factor there. And we would then divide by 760. Will convert us into atmospheres. So 721 divided by 760, not by itself. I should probably put the calculator down for today. 0.94, we'll go with 9, looks like a winner there. Atmosphere is the partial pressure of the oxygen gas. And again, sometimes in labs, they will kind of refer this to as the pressure of like the dry gas. Again, the idea there is you're subtracting off water, basically. So sometimes in laboratories, they oftentimes will refer to it as, again, that pressure of the dry gas. Any question on sort of partial pressure? So we've seen sort of 3 different situations where partial pressures can kind of come about. One sort of a regular situation where we just ideal gas law, one not so regular where we can't use the ideal gas law but have mole information. And again, this is a very common sort of partial pressure situation. Any questions on any of those there? Okay. So next thing we're going to talk about is some of the stuff that we've sort of touched upon as we've gone through several parts here of the gas chapter here. And this is the kinetic molecular theory of gases. And basically gases, right, are composed of molecules that are separated by very great distance from each other. Again, they're flying around. We think about these sort of molecules as they're flying around as sort of points in an ideal situation, and that they possess mass, but they have what is referred to as a negligible volume. So the volume of the gas itself is thought of as being 0. So if you remember, maybe I mentioned it the other day as well, that one sort of important aspect of something that's considered an ideal gas is basically the idea that although, the gas molecules are flying around, they have mass, the volume of the gas molecule compared to the volume of the container at which they are flying around, the container usually is a much, much, much larger sort of volume. And since they're flying around and they fill that container uniformly, we sort of, in an ideal situation, think about the gas as having the same volume as the actual container. And that's why when you look at a lot of sort of ideal gas law sort of problems, or just gas law problems in general, and if you look at the volumes, oftentimes the volume is referred to a lot of times as the volume of the container that the gas is in, rather than the volume of the gas itself. So that's one thing that makes something sort of a ideal gas, is the idea that, basically it has sort of a negligible volume. Gas molecules, as we've been talking about, are in constant motion. They collide with each other. Collisions among molecules are thought to be perfectly elastic. They're not sticking, right? They're just going to kind of bounce off, move around. Everybody's okay, even though they're bumping into each other. Again, collisions really is what sort of causes pressure. But again, we're having sort of no influence on each other as they're moving around is another sort of ideal sort of situation. And number three really is sort of the second part of what makes something an ideal gas is that gas molecules don't exert any attractive forces or repulsive forces upon one another. So this part of it here again is sort of what makes something, these two guys is basically what makes something an ideal gas or is considered an ideal gas. Why would sort of them having no attractive forces or repulsion type forces be important in an ideal situation? It has a lot to do with sort of what we were just talking about in a mixture of gases, right? So if we have a mixture of different gases in the container, and this gas molecule is on its way to sort of collide with the wall, but in a non-ideal situation, there might be some attraction between these guys. So what's that going to do? Well, it's going to kind of reach out and slow down that gas molecule, right? He's going to kind of feel a little drag perhaps. And that would affect obviously his collision rate and how hard he would hit the container as well, the pressure associated with that. He may also feel like a repulsive type force, right? Which means he may go the other way a lot quicker, which also would have a lot of effect on, the collision rates and sort of what's happening. But in an ideal situation, we assume that there is no real intermingling, if you will, of the different gas molecules. They're flying around, one's not affecting the other. And that's why what we just did with the partial pressure calculations, why we could simply just treat each gas like they were in there by themselves and do an ideal gas law is sort of this ideal situation that, they will have really no effect on one another. There are certain situations that we'll talk about at the end of this chapter where that is not the case, and they actually do sort of impact one another, and also their volumes are not considered zero. And that's what we're going to talk about at the end, which is what we refer to sometimes as real gases, unlike those fake gases we've been talking about. But they're sometimes referred to as real gases. And under real gas situations, as we'll see a little bit later on here, you do have to actually take those things into account, both the volume and the attracted and repulsive type forces. But under sort of normal conditions, kind of 25 degrees Celsius, 1 atmosphere type conditions, most things can behave sort of ideally and be thought of as behaving ideally. And again, those are the two things that really sort of make something an ideal gas. Last thing there is the average kinetic energy of molecules is proportional to the temperature. So obviously, the higher the temperature, right, the faster the guy's going to be flying around, has more energy, and vice versa. Obviously, if you lower the temperature, not going to be flying around a lot as fast. Here are some of the ideas that we talked about along the way with all these different gas laws and sort of relationships. Again, gas is very compressible. We have Boyle's law, right, which basically showed that as one goes up, one goes down in turn, pressure goes up, volume goes down, and vice versa, sort of that inverse relationship. We talked about Charles' law, Guy-Lussac's law. Again, basically as the temperature goes up, so does the volume. In a Charles' law situation, if the temperature goes up in a Guy-Lussac's law situation, pressure goes up, again, because the volume is not adjusting. Avogadro, our good friend, about the relationship between really sort of volume and moles are the same. And as we just talked about here, really are partial pressures, again, a sum of all the individual sort of pressures happening there in a mixture of gases. Any questions on the kinetic theory of gases? Okay, then we're going to actually talk about a little bit about sort of the speed of molecules and, how we can kind of test molecules and determine, what affects sort of the velocity or how fast the molecule is sort of moving. So let's take a look at a couple of charts here and kind of look at the differences here between them. So on the left, what we have is nitrogen happening here. So this is nitrogen gas. And we have nitrogen gas at some different temperatures. So we have nitrogen gas at 100 Kelvin, 300 Kelvin, and 700 Kelvin. And what we see is on the left sort of the number of molecules, and we see the speed. So if we just kind of go over the big part of the curve there coming down, we see that, you know, at 100 Kelvin, we have basically a molecular speed. Most of the molecules are basically in this range. We increase the temperature a little bit to 300 and kind of come straight down. Very badly done here. We do see here that the average sort of speed there is in this range. We increase the temperature even more to sort of 700, taking sort of the peak here. We see that again, the temperature, the speed increases. So what we see is if we look at the same gas, but we increase the temperature, we're actually increasing the actual speed of that gas molecule. And these are meters per second, by the way. And that's what we see if we look at just one gas. Over here, what we're looking at is actually the temperature remaining constant, but we're looking at 3 different gases, right? So we're looking here at 3 different gases. We have our chlorine, we have our nitrogen, and we have our helium. And again, if we sort of analyze it the same way, kind of coming straightish down there, that's going to be what's happening with chlorine at the 300 Kelvin. For our nitrogen, kind of coming down straight-ish in this range. But we do see over here our helium kind of at the peak way down the road here in terms of its actual speed. So what is the difference with this is sort of what we talked about on that previous example. If we do a comparison of our molar masses, we see that chlorine at 2 chlorines, 70 grams per mole, is much slower or moving much slower at the same temperature of nitrogen. That's only about 28 grams. And nitrogen is moving much slower than our good friend helium here, that is much, much lighter. So what we see is that as the molar mass of a gas decreases, the molecular speed of it actually increases. And we could actually calculate that, and that is what is known as the RMS, or the root mean square velocity. That is a mouthful right there. That is the root mean square RMS velocity. The root mean square velocity is calculated with this formula here, which is 3 times R times T divided by the molar mass. So let's talk a little bit about this formula. First off, R is the gas constant, but it is not the gas constant that we use with the gas laws. It's actually the gas constant that has energy associated with it, 8.314 joules per Kelvin per mole. So the R here is a gas constant, but it's not the one that we use, the 0.082. You don't want to use that one, otherwise your number will be off. Obviously, we're in there. T is temperature in Kelvin. And again, the M there is the molar mass. Now, normally when we do molar mass, it is grams per mole. In this situation, it actually needs to be kilograms per mole. You may be wondering, why does it need to be kilograms per mole? It needs to be kilograms per mole because of the R value here. When we look at a joule, 1 joule, which is what a unit of energy is there, is equal to a kilogram times a meter squared divided by a second squared. So kind of like what we saw, I think, what was that thing? We saw that thing in way back when, the de Broglie wavelength, I believe. We saw something very much like this, I think. It does need to be in kilograms so that these kilograms do cancel out. Again, if we look at just sort of the units going on in there, we kind of do the big square root. We have R, which technically is joules, which is a kilogram meter squared second squared divided by Kelvin and mole. And that gets us the T, which is Kelvin, all divided by kilograms per mole. The kilograms cancel, the moles cancel, the Kelvin cancel. It actually leaves us, if you look in the square root, the only two units left are meters squared over seconds squared, which obviously when we take the square root of that gets us to meters per second. So good news on one of these things is R is still that 8.314. You don't change the number. The units is really just kilograms, meters squared, second squared. But the only one that you really got to watch out for is sort of the molar mass. It does need to be in kilograms per mole to allow that to basically cancel out correctly. Yeah, so this equation allows you to find basically how fast a gas is traveling at a particular temperature. So that's the root mean velocities. The root mean square velocity is basically how fast it's traveling. It's basically how many meters per second is that gas basically traveling, is what this will allow you to calculate. Question on that there. So why don't we try, actually, let's just do the two that we looked at earlier. So that was a mixture of helium and neon, right? So what is the root mean square velocity for helium and neon? And I believe we'll just do it at 25 degrees Celsius. So why don't you take a couple of minutes here and see what you calculate. Let's get two answers. What is the root mean square velocity in meters per second of helium and neon at 25 degrees Celsius? A reminder again, helium was 4.003 grams per mole and neon was 20.18 grams per mole. All right, take a couple minutes, see what you come up with. We'll start with helium. So we're going to do the root mean square velocity for helium here. That's going to give us the square root, we'll make a giant square root, of 3 times our 8.314. Again, if you want to see the units, you could swap out the joules for kilograms, meters squared, seconds squared, still would be Kelvin and mole on the bottom as well. Our temperature would need to be converted to Kelvin, so that's going to give us a 298 Kelvin there. That's going to then be divided by the molar mass of helium. Remember, though, that we do need to do a conversion here so that everything cancels out correctly. So that's in grams, and there's 1,000 grams in a kilogram, which means we need to divide that number by 1,000 or move the decimal place, and that would get us looks like 0.04003 kilograms per mole. Again, the kilograms are necessary here to really get rid of the kilograms that are represented by the joules. Again, the Kelvin will cancel, the moles will cancel. Looking at our units, we are left with, again, meters squared divided by seconds squared, which is exactly what we're looking for here. So 3 times 8.314, again, not the one we use for the gas laws, divided by our 0.004003 gets us a big number that we square root. We don't want to forget to do that. And roughly speaking, we have our helium molecules at 25 degrees Celsius flying around at 1,363 meters per second. That's fairly fast, yes. So let's do a comparison here to our neon and see how it's doing. So if we do the same thing here for neon, basically putting it into the same equation. So we'll make another big square root. 3 times our 8.314. Again, swapping out those units so we could see them sort of cancel. Temperature still the same as 298. Same deal with the molar mass here. We've got to make sure we get it into kilograms so it properly cancels. Basically divide it by 1,000 or move that decimal point over. Looks like we will end up with 0.002018 kilograms per mole. Again, moles cancel, Kelvin cancels, kilograms cancel, leaving us our meter square, second square. That is a 3 times 8.314 times 298 divided by 0.002018. And again, not forgetting to take the square root like I almost did there. That's going to get us a value here of, just want to make sure, I think I put an extra 0 in there. I am not having a banner day here with the calculator. I did. I put an extra 0 in there. All right. Well, we'll just erase it and pretend I didn't do that. We'll edit that out in post editing, I suppose. All right, let's try that again with the right number there. At least I recognize it, I suppose, that it didn't look right. All right, 0.02018 would be what you get when you divide that by 1,000. Now doing a little square root action. That's maybe more like it. How about 607 meters per second would be how fast our neon gas is basically flying around. First off, any questions on the calculations there? Now, if you remember that sort of partial pressure problem we did not too long ago, a few slides back, it was a different temperature, but roughly speaking, the helium contributed to like 12.3 atmospheres versus the neon, which contributed to 2.4 atmospheres. And again, this is one of the major reasons why in that sort of problem, helium would contribute to more pressure. It is moving about 2 times as fast as the neon molecule is moving around. Again, because it's moving around faster, it's lighter, it's going to be resulting in obviously more collisions, contributing to more of the pressure that we would associate with that. And again, if you wanted something like miles per hour, you could do that conversion as well, like 3,000 miles per hour or something like that, you know, so it's moving very, very fast. Any questions on how to calculate sort of the root mean square velocity of a gas? Okay. So another sort of thing we're going to talk about here is what is referred to as gas diffusion. And gas diffusion is the gradual mixing of molecules of one gas with another based on their kinetic sort of properties. So we got a couple of containers here. We got a container of ammonia, which is a gas. We got a container of basically hydrochloric acid, which is hydrogen chloride when it goes into the gas phase. And when they come together, they make a compound which is known as ammonium chloride. So what we see when we look at this is we actually see the mixing happening over here, right? So all the mixing is sort of happening over this side, closer to the HCl sort of container. And why would that be? It would be based on what we were just talking about a second ago. If we do a quick comparison of molar masses here, 17 versus 36, and if we had to roughly estimate, I would imagine that the root mean square velocity of ammonia would be faster than HCl, which means when the ammonia exits the bottle, it is moving much faster, which means it's able to get over here a lot faster than the HCl, which is moving a lot slower out of this bottle. And that means that all the mixing that's going to occur to make the product, that white stuff that was there before I scribbled all over the place, is actually going to happen closer to the slower moving gas. And again, that's based on sort of molar mass here. And again, that's why we anticipate the mixing happening in that situation. You could actually sort of calculate some of these things with R1 over R2. That is a rate 1 over rate 2, you know, meters per second, something how fast it's moving. Is equal to the square root of the molar mass. And in this case, you can leave the molar mass, in this case, as grams per mole. There's no R involved here. They're both molar masses, by the way. Molar mass of gas 1 and molar mass of gas 2. Again, you could figure out how fast, you know, one gas is moving versus another in terms of the rate. If you know the rates of both gases and one molar mass, you can figure out the molar mass of another gas as well. But this sort of gas diffusion or mixing that's happening, again, in this case, happening closer to the slower moving gas, because really the ammonia can move a lot faster and pretty much get over there a lot quicker, and allowing the mixture to sort of happen, or the mixing to sort of happen near the other guy. Another sort of relationship in terms of things moving and how fast things are moving is what is referred to as gas effusion. And gas effusion is the process by which gas under pressure kind of escapes from a hole. So we have a whole bunch of gas over here, a little kind of negative pressure on this side, and a little hole where pop out. We could get some gas molecules popping out from the other side. We basically can use almost the same equation that we got going on over here. We have the rate 1 over rate 2 is equal to, we could also do time, like how long it takes one gas versus the other to get there. Our same thing as we saw before, our molar mass on the other side. So we could use this equation for a couple of things. You know, for example, if we look at sort of the problem that's on the bottom there, we have nickel forms a gas compound with a formula of NiCOX. We're not really sure what X is at this point. What is the value of X if under the same circumstances, methane, which is CH4, effuses 3.3 times faster than this compound? So you could make things whichever ones you want. So for example, we could get the molar mass of this guy, which is one of our sort of gases. So that would be 12.01 for the carbon plus 4 times 1.008 there for the hydrogen. That gives us a molar mass of 1604 grams per mole. Molar mass of this compound is, I'm not sure, because we don't know what X is, so we don't really know that. But we do know that if we call, let's just say we'll call CH4, we will call that M2, which means that the rate of CH4 will be R2, and it will be 3.3 times faster than R1, right? And we'll call the rate of this guy R1, so we'll call this guy M1. So we don't know what the rate is, but we do know that the second guy is basically 3.3 times faster. So if we sort of put our numbers in there, what we got there? We got that R1 divided by R2, which is 3.3 times R1, is equal to the square root of, I called CH4M2. So you could do it any way you want, but I went with this way. So we'll get some weird math there. And this is what we're looking for, right, is the molar mass of our compound. So this guy and this guy cancels. That essentially gives us 1 over 3.3 is equal to the square root of 16.04, and again, M1. To get rid of the square root, we actually need to square both sides. So I'm going to take 1 divided by 3.3 and then square it. If I put the other number on top, I would have had a much prettier number, but oh well. So 0.0918 3 is equal to 16.04 grams per mole divided by M1. And again, what I did here is I squared this and I squared this at that point. I'm going to multiply the M1 to the other side and divide my number that's on the other side back over. And if we do all that good stuff there, we end up with a molar mass for our unknown compound of approximately 174, we'll call it 7 grams per mole. First off, any questions on that calculation? Okay, so how does that help us sort of determine what is missing? Well, if we look at this formula, let's just take an accounting of this formula here. There we go. The one thing that we know for sure is we definitely have 1 nickel here. So we actually could go to the periodic table, look up nickel, that's 5869. So we can actually take our molar mass that we calculated for this compound. We could subtract 58.69 from it. And if we do that, we are left with approximately 116.01 grams per mole. That is made up of these CO units, right? We have 1 of them, 2 of them, 3 of them, however many of them we have. But what we know about each of these CO units is carbon is 12.01, oxygen is 16, which means each of these units are basically 28.01. So I know the 116 is 1 of those units, 2 of those units, 3, 4, 5 of those units. If I take 116 and divide it by 2801, I end up with approximately 4.14, which is approximately 4 in this case, which would tell us that the proper formula would be NoCO4 in this case. Any questions on that calculation there? So again, you could use this formula obviously to figure out a formula like we just did here. Again, you could figure out if you know the molar masses, how fast the rate is. If you're dealing with time instead of rate, you can figure out how long it would take a gas to kind of move from one side to the next. Any questions on that there? Okay, so the last thing we're going to talk about here in this chapter is actually we're going to now talk about sort of the idea of real gases. So up until this point, we talked about ideal gases, and we pretty much have considered everything that we see pretty much ideally. But under certain situations, as we'll talk about here, some gases don't behave ideally, and these guys are sometimes referred to as real gases. When does this occur? Well, this occurs sometimes at very high temperatures and very high pressures as well, as where we kind of see these things come into play. If we look at the ideal gas law and we solve for N, which is PV over RT, in sort of a perfect ideal relationship here, our situation, we get a ratio of 1. But when we get to really high pressures like we have here, right? Super high pressures, like 1200 atmospheres. We start to see some gases really deviate from an ideal situation. And that's because what happens under really high pressures is the gases actually do start to interact with one another. So if you remember just kind of from Boyle's law, as pressure goes up, right, what happens to volume? It goes down, which means in these situations of really high pressures, we're pretty much squishing that volume way down, which means that those gas molecules now no longer have a lot of room to move around. And just by proximity, you can see that they are definitely hanging out near each other for a lot longer period of time. So because of these really high pressures in these situations, our gas molecules are no longer able to just go, I'm not really interacting with you or anything like that. I got my own space. I'm okay. There's no choice in this situation. They're in this really small volume. They're going to be near each other for a lot longer period of time, which means we do start to see some repulsive forces, which means they don't want to be near each other, and even some attractive forces sort of happening with these gas molecules. And we get to see really some deviation from sort of this ideal situation because of this. Now, let's talk about sort of reality and why we, sort of think about most of things as ideal gases, right? And why do we consider most things as ideal gases? Well, under normal pressure, it's nowhere near here, right? Normal pressure is like 1 atmosphere, which if we look at this chart is like right there, right? And you can see right there at where we normally in normal conditions deal with gases, there's not a lot of deviation happening from that line. A little bit, but not a tremendous amount. So under kind of really normal, run-of-the-mill pressures of 1 atmosphere in that area, there's really not a lot of deviation that's occurring between the different gas molecules from a sort of an ideal situation, which is why we can apply that ideal gas law to pretty much all gases. And it's really more of a universal gas law at that point because we don't have to adjust for different gases. As we'll see here in just a second, all these different gases have some different deviations, which make you, for the individual gas, have to sort of, adjust individually based on the gas that's present. So under normal conditions of pressures, which is closer to 1 atmosphere, we do sort of assume a lot of times this ideal situation because, there is some deviation, but there's not a tremendous amount like we have, over in this area when we really get into some really, really large sort of pressures. So the difference here again between sort of that ideal versus real gas situation is, and I know we're towards the end here, so we don't have very much to go. So I'm just going to finish it up here and we'll kind of start lab just a little bit later. That way we don't have to stop and start and stuff like that. But ideal versus real gases, again, often don't behave like ideal gases. And it's really at these situations where we have these really high pressures and kind of low temperatures. And I may have misspoken a second ago, is high pressure and low temperature. And the two things, if you remember, really of what makes something an ideal gas is, again, that idea that there's really no attractive forces or repulsion forces between gas molecules, but also that they don't take up any space. They have basically a negligible sort of volume. And under these conditions of high pressure and low temperature, we don't really sort of witness that happening. We see some deviations from our STP, right? If you remember, 1 mole of any gas is 22.414 liters. So when we start getting some deviation here of our molar volume under these conditions, again, these gases are no longer sort of behaving ideally. We just talked a second ago about sort of high pressure. Let's talk about sort of here, and we'll talk about it again in just a second. But what happens at low temperatures? At low temperatures, our gas molecule is definitely going to be moving slower, right? Which means if we have a couple of gas molecules near each other, this gas molecule is going to take longer to sort of move past this gas molecule because they're both moving a lot slower. That means that they're going to be in contact with each other for a lot longer period of time. And a lot longer period of time means that they are also going to interact with each other for a lot longer period of time because of, they're just moving across each other slower. Like if two people are walking by each other at a very slow pace, they're near each other for a lot longer period of time. Somebody's running past you, obviously they're moving past you a lot faster. So again, that's going to cause a lot more interaction, as we talked about with that high pressure, going to result in that low volume. In addition to that low volume, the idea of the volume of the gas molecule itself does come into play here as well. Again, if you think about it, in a larger volume, you got this gas molecule, you know, relative size of that, or volume of that gas molecule to the container, is pretty negligible, right? The container itself is much, much larger. When we squat down that volume much smaller and you have that same size gas molecule, now the volume of the gas molecule is sort of relevant to basically our volume of the container which it's in. So, the pressure and the temperature plays a very big role in that effect. So at low temperatures and high pressures, again, these sort of ideal situations are not really valid anymore. So let's talk about some of these things that we see that are a little bit different. Because real molecules do take up space, what we see is that their molar volume of a real gas is actually larger than what would be predicted under an ideal situation. And that's what we see here. Again, sort of in normal sort of pressure situations, 1 atmosphere way over here towards the line, but you can see the two lines are pretty much on each other. It only starts to separate out here as we start to see the pressure, right, starting to increase, and we get higher pressure. Now we're getting some more deviation between those two lines. The red line is ideal situation, argon here in more of a real gas sort of situation. And this is the molar volume. So we see the actual volume of the gas is starting to be significant as we get into these higher pressures, again, because it's sitting in usually a much smaller volume. So, it's going to take up obviously a lot more space. Now, the effect of that is what we have happening is at these high pressures, because the amount of space that's occupied by the molecules is relatively significant, the molecular volume of a real gas is again larger than would be predicted by that ideal gas law. So our good friend van der Waals, who we'll talk about in the next chapter as well, did a lot with intermolecular forces, basically how molecules interact with one another. He basically took the ideal gas law and created a correction value for this. And this is what is referred to as van der Waals constant B. And it takes into account that difference in the volume that we see for the ideal gas law, sort of incorporating into the ideal gas law this sort of constant. Now, the volume difference that we see here is accounted by that constant. And there's two constants, which is A and B, and we'll see the next one here in just a second. These are what are referred to as van der Waals constants. And we find these values actually in a table. And the problem, though, or sort of one of the aspects of this is they are different for different gases. So it's not necessarily like one value for B for everybody. Every gas has sort of a different value for B. And again, now we're getting into more of a non-sort of universal gas law like the ideal gas law, to one where now we have to find specific correction values for these situations for these kind of individual gases. So that's one aspect that obviously real gases are different. Again, that volume. In addition, we see that the molecules will actually be attracted to each other or repulsed by each other under low temperature. So that's what we see here. Under sort of, high temperature situations, those gas molecules are moving really fast, which means they are basically running by each other in my analogy. When we kind of lower those temperatures down, again, those gas molecules are now walking past each other, and they're now in contact with each other over a longer period of time as they're flying around. Again, we're going to get that interaction that's going to happen between one gas molecule and another. They're going to be perhaps attracted to each other. They may actually be repulsed by each other, but there is going to be a difference in how they interact under these conditions versus sort of ideal conditions, because they're essentially just not moving as fast. So they're in contact with each other for a longer period of time. So van der Waals as well took into account that and came up with sort of a correction value for those intermolecular forces or attractions. Intermolecular forces means the attractive forces between one molecule and another. So one molecule and another, attractive forces. That's what intermolecular forces. They're basically the forces that hold one entire molecule together with another. And again, he came up with sort of this correction value on that. That's going to affect sort of the pressure aspect of our situation. Because again, as I was mentioning, we'll see a much better picture in just a sec. If there is some attractive forces between molecules, and as this guy tries to get away, he's going to kind of feel some drag, if you will, because he's got some attractive forces happening to, say, the molecule behind him. That's going to cause perhaps the guy not coming into the wall of the container as fast. It might take longer for collisions to occur. All those things are going to have an effect on the pressure. And we would see that the pressure would be less than what we would assume it to be in an ideal situation. And again, it's because of these intermolecular attraction or attractive forces between these gas molecules that are essentially flying around. Here's a much prettier picture of that again than what I drew. But our red sort of gas molecule wanting to basically hit the wall, feeling some of the attractive forces from those green molecules are going to kind of slow its roll into that wall. And again, going to take a little bit longer perhaps for the collision to take place. It might not collide as strongly as it would in an ideal situation. So here in the real gas situation, that's what we sort of see here, or an effect on the pressure because of those attractive forces. So we have an effect on the volume because of those the pressure, and we also have again here an effect on the pressure because of those attractive forces that are happening. So what does that mean? How do we correct this? What do we use? We used a really scary looking guy, which is known as the van der Waals equation for real gases. How does this sort of formula work? Well, it works pretty much like the ideal gas law, except it looks scarier. So basically inserting our corrective sort of values, if you will, to correct for the pressure and to correct for the volume using our van der Waals constants. Again, basically they're put into the pressure and volume part of the ideal gas law. Everybody else here is pretty much the same. That's pressure in atmospheres, volume in liters, moles, volume in liters, moles, gas constant 0.08206, the temperature in Kelvin. Everything's the same, except again, we have sort of those correction values that are there. And here's again our van der Waals constants, which you typically would find on a table. If you ever have to look up these guys on a table, it's really important. A couple of things. First off is units. You always want to make sure the units are sort of the right ones. Sometimes they're weird units, so you might have to do some conversions, but probably in textbook tables, they'll be the right units, I'm assuming. But you can see here, though, there are different values for different gases. And obviously, the A and B value for helium is different than obviously the A and B value for argon, right? And this is what I was talking about kind of a minute ago or a little bit ago, which is, this is why under kind of our normal situations of 1 atmosphere, if you remember that first chart, we're way back here where there's not a ton of deviation happening from that ideal situation. That's why we oftentimes will assume sort of ideal gas sort of situations. Again, it's more of a universal sort of formula that we could use without having to worry about, oh, am I dealing with helium today or am I dealing with argon? In an ideal situation, you don't have to worry about those things. In a sort of real gas situation here, you do have to take those into account. So this is almost a more non-universal type of formula to be used. It is so really gas dependent, right? Because you have to look up these values for them. So clearly this table would be provided for you if you had to do some type of calculation with this. But you do plug it in here just like you normally would anything else, and you could solve for anything just like normal. It's a little bit more scarier sort of parts here that are these corrective values. So this is the formula that you would use again in these sort of real situations, which, as we talked about here, is basically high pressure or low temperature type situations that are happening. And again, under these situations, really the real gas sort of kicks into effect, and you do have to use that. But again, the good news is probably 99.9% of the time, we could assume more of an ideal situation and use our ideal gas law. Any questions on that there? Okay, that then actually does wrap up. That's good. That wraps up this chapter, which is chapter 8. And again, that is the last chapter that will be on our exam, which will be 1 week from today. And that means that we